Welcome everybody to this week's STEMS webinar. So we are very happy to have Michael Wehner here as a speaker for this week. So he's a senior staff scientist at the Lawrence Berkeley National Laboratory. His expertise is in climate science and is especially interested in extreme weather events under climate change, so things like tropical cyclones, extreme precipitation, heat waves, and related things. And he's looking at both using models and data and kind of statistics in between. So kind of the whole big picture. In addition to that very high impact work, he has been very active in leading this international and national climate assessment. So he has been the lead author of the last couple of IPCC assessment reports. And he's also been the lead author of many of the recent US national assessments of climate change. So doing very important work in that front. In addition, he's one of those climate scientists who really likes to talk to statisticians. So he has collaborated a lot with statisticians, and I've actually met him in multiple statistics workshops. So he definitely likes to talk to our community and has interacted with us a lot, which is great. There's always need for people who work at the intersection of statistics and climate, and Michael is one of those. And he's also, for example, the editor of the Ask More journal, which is the journal on the advances in statistical climatology, meteorology, and oceanography. So also in this kind of interface between statistics and climate science. I also learned that his background is in physics. So his bachelor's degree is in physics, and then his advanced degrees are his master's and PhD degrees are in nuclear engineering. So very well fitting for STEM's webinar. So today we will be hearing about his recent work on attribution of extreme weather impacts. So Michael, please take it away.
Well, thank you, Mikhail. Just share the screen. Okay, and you can see that, I hope.
Yeah, looks good.
Okay, good. So I'm going to talk about something we call extreme weather impact, extreme weather attribution, and in particular the impacts of extreme weather and how to quantify the human influence on not just the weather, but on what happens to people. And I know that this is a statistics seminar. I'm not a statistician. I work with statisticians a lot, as Mikhail said, but there'll be no theorems or proofs or lemmas or anything. But there is some statistics that you'll see. And I hope to share with you the need for advanced statistics in the climate sciences in general and in attribution science in particular. There is an awful lot of interest in this kind of field. Considering how small it is, it's kind of crazy. In fact, my week has been turned upside down. I just got off vacation and then was invited to testify to the United States Senate Committee on Environment and Public Works on Tuesday on this very subject. And so there'll be some more of this online if you're interested. It will be interesting to see what questions they ask of me. This is Hurricane Harvey, or the flood after Hurricane Harvey, actually, in the part of Houston, Texas. And I'm going to use Harvey as an example, one example of a few, to illustrate what I mean by all this. So first of all, the most important slide is I'm speaking on my own behalf, not that of the Lawrence Berkeley National Laboratory, the University of California, or the United States Department of Energy. So what is this thing, extreme weather event attribution? Well, basically it's two questions, and they're these. How is the probability of an event change because of climate change, and how did climate change affect the magnitude of this observed event? And these are really two sides of the same question. And I show this simulation here of two worlds. One is in red, the real world, with everything that we can do in a climate model to make it as realistic as possible. So it has all the greenhouse gases, and it has all the aerosol forcings, it has all the solar forcing, the volcanic, everything that we think is important for the climate that we can model is in the red curve. In the blue curve, it's a counterfactual world where we don't change the human changes to the composition of the atmosphere. So there's no change in the greenhouse gases, there's no change in the aerosol forcing, but there are changes in the volcanic forcing and in the solar. And you can see that what I've plotted here is the return value of temperatures in the Pacific Northwest of the United States that was prepared for the 2021 Pacific Northwest heat wave, which I'll use another one I'll use as an example later. And so the first question, we would fix the magnitude. Let's say that we had a 100-year event, which in this place would be 106.8 degrees Fahrenheit. And we could say, okay, this is the second question, I'm sorry, we're fixing the probability. And so what was a 100-year event in the world without climate change? And we see from in this simulation, it was about 2.5 degrees Fahrenheit cooler. And so we would say, that climate change increased the magnitude of a 100-year event by about 2.5 degrees in this region. The other question, the first question, is the change in the probability. So there you would say, okay, we experienced 106.8 degrees. That's a once in a 100-year event. What would that have been in the world without climate change? And so we go to the horizontal direction, and you can say, oh wow, that was a 1 in 1,500-year event. And so we would say that climate change made a temperature of 106.8 degrees 15 times more likely. And we often refer to that, the ratio of probabilities. We call it the risk ratio in the literature, and I'll use that term again later. So that's basically it. But I'll get back to this question in a moment. So that's about the weather, but the impact of that change in the weather can be substantial. And so questions of extreme weather impact and how humans might have affected those impacts is, how much did climate change cost, in this event? Or how many people died because of climate change in this event? Or even more personally, did climate change flood my house? I've had this question asked of me. Or did climate change kill my grandmother in a heat wave? These are legitimate questions. So, some of these are tractable, some of these are only answerable in a probabilistic sense, but others might be yes or no questions even. So I mentioned that I was going to use Hurricane Harvey, and this is the picture you saw. This is Hurricane Harvey from a satellite, just as it was making landfall on the Texas coast. And you can see it's a massive storm that was large and was unusual because of its track. And here is a picture from the National Hurricane Center showing the track. And the numbers are the days of the month, starting in August. And you can see that around August 25th or so, it approached the coast and it just hung out there and stalled, completely stalled. And as it did that, let's go back one. As it stalled, it would pick up moisture off the Gulf of Mexico and then dump it over land. And it did that for 4 or 5 days. Some places received 5 feet of rain in the week of this storm, which was just astonishing when you think about that. So the first question in this chain of events this chain of thought of attribution statements from the weather to the impacts and then to environmental justice at the end, we'll start with the weather. And so the Gulf of Mexico was warmed by climate change by about 1 degree centigrade. And as I mentioned, there was copious amounts of precipitation in this storm. Now, as it turned out, there were 3 independent groups, one of which was myself and Mark Risser, that studied this storm. And in fact, 2 of them came out on the same day. The storm was in August, September, and the papers came out in December. So it was one of the most, at that time, one of the most rapid attribution studies, and actually a pair of them. And all 3 of these had a surprising result, and I'll come back to this, that the change in the rainfall exceeded the thermodynamically constrained change in the available humidity. That's the Clausius-Clapeyron relationship, which is a 19th century relationship that was developed to make steam engines more efficient, that tells us that for a degree centigrade of warming, the saturation specific humidity can only increase by 7% or so. And so we would expect that the available moisture for this storm was increased by global warming by 7%. But you can see the numbers that I have here in red are the estimates from these three studies of how much climate change increased the precipitation. Mark and I found a 24% increase. My friend, the late, great Gert-Jan von Oldenburg, found a 16%, which is twice the Clausius-Clapeyron. And Simon Wang, who I didn't even know at the time, did another study showing a 20% change. You can see here the actual station data here. Then it was smoothed by us to make a graph, and you see that's actually consistent with an independent radar-based measurement. But I want to take an aside here that I hope is interesting to statisticians, and that is that basically this exercise of extreme event attribution is an exercise in causal inference. And because these two questions that I asked, the defined event attribution, are basically a reflection of the fact that complex events like a storm or a heat wave or what have you have complex causes. And so, it's not always, if you hit your thumb with a hammer, that obviously was the hammer that did it. But these complex events have multiple causal agents. And so we borrow techniques from epidemiology. And the first one is what I'm calling Pearl causal inference. Professor Judea Pearl, a professor emeritus at UCLA, wrote a very good book on causality, and it's actually, his theories are somewhat more comprehensive than what I'm going to say here. But I'm going to call Pearl causal influence where you do a direct interference in the experiment. And so in epidemiology, you would take two groups of patients who are similar, that have some affliction. You would give half of them the medicine and half a placebo, and then compare the two groups and see how they respond. It's because we only have one planet. We have these models, and so we have simulations that I showed you before of the world that was and the world that might have been, the counterfactual world without climate changes, and we compare them. So that's a direct interference. I'm going to label that kind of philosophy a Pearl causal inference. The other strategy is to not use climate models at all, but just go to the observations and build a statistical model and postulate possible causes with covariance. And this was first espoused by Sir Clive Granger, who won the Nobel Prize in economics for that. And we're going to label that kind of inferential, as opposed to interference, kind of a statement as a Granger causal inference. We'll go back to Harvey and do some examples. Now, Simon Wang, the third paper in that, he's at Utah State. He ran a model called WRF, the Weather Research Forecasting Model, and he downscaled some of the weather prediction data. So it's a hindcast, and he ran the storm that was, and then the storm that might have been without warming, and compared the two. And we call this a storyline because it's a very constrained kind of simulation. And he found that climate change increased the precipitation by about 20%. Gert-Jan did what I call a very traditional kind of Pearl causal inference. He did not use a storyline. Instead, he took long climate model simulations and used the statistical model on the observations to estimate a rarity, then went to the climate models and said, how much did an event of that rarity in these climate models change? So that very first question, fixing the rarity, estimating the change of magnitude. And he came up with a range in the IPCC calibrated language, a likely range of 8 to 19%. And you can see he did it for each of the three models, and this sort of synthesizes. And this is what the World Weather Attribution group that you may have heard of does routinely. He and Gert-Jan and Freddie Otto founded that. Gert-Jan passed away about 2 years ago. He was a very good friend of mine, and I miss arguing with him all the time. We did not see have the same point of view, but we always learned from each other. And then Mark and I did a purely statistical exercise, the Granger a causal inference, as I'm labeling it. And we took a generalized extreme value distribution to model the observations in these ellipses or of the observations over Texas. And we used two covariates. One to represent the human causes, that would be the log of carbon dioxide in the atmosphere. That's shown to be what temperature is proportional to, and then El Nino, an index for El Nino, because we know that El Ninos control Atlantic hurricane activity. And what we found is that this was a very rare event, even with climate change, in our smaller region where the 5-foot rain was happening. We found it would be a 1 in 3,000 year event, and in the larger region, it was about a once in millennia event. And we did find well, I'll get back to that in the next question. And so we then said, let's do what we call the statistical counterfactual. And so we fix we calculate the probability at using the 2017 levels of El Nino, but 1950 values of the carbon dioxide. And we found two things. One was that the magnitude question in the small region was almost 40% increase in this most intense part of the storm. And in the larger region, about a 24% increase. So somewhat larger than the other two, but our confidence intervals overlapped in all three of these studies. We also found that the risk ratio, so if we looked at the observed amount and said how much, what was the probability of that in 1950, that changed by about a factor of 10 or so. And so just to go back to this, for a long time, this result really puzzled me. How could the storm produce more increased precipitation? How could that be more than the increase in available humidity? And I finally realized it wasn't anything magical. What it is that the storm is just a little bit stronger because of the extra energy from that 1 degree of warming. And so the winds are a little stronger. And that means that the updrafts are a little stronger, which means that the storm is more efficient. More intense storms are more efficient at raining out the available precipitation than weaker storms. And so we have a plausible physical mechanism for why these estimates exceed this Clausius-Clapeyron scaling relationship on humidity. And we've looked at about 30 different storms. This was the first storm. It was, pardon the pun, a watershed event in attribution of hurricanes, because it was the first one to really be looked at seriously. We've looked at probably 30 or 40 different storms now, and it's always super Clausius-Clapeyron. So the next step in this chain of attribution statements is, let's go from the increase in the rain to what did that do to the flood? And so we did a storyline analysis. And we already had, I met this fellow, Chris Sampson, who works in Bristol at a company called Fathom, and he already had a simulation of the flood that was driven by this data set that you see there for the precipitation. And it was, they wrote a paper and showed that it was a quite realistic simulation of the flood from looking at satellite observations of the flood. It lasted long enough that the skies cleared and satellites could see the extent of the flood, so it provided good validation. And so I asked him, I said, could we do the floods that might have been? And we could take those rainfall estimates of the change and just alter this rainfall uniformly by these statements as a simple kind of thing to do. And so, for example, in our 24% increase due to climate change in the precipitation, let's decrease it by 1 over that. So about multiply the actual values by 80%. And we did this actually for all of the published statements. And here's an example of what happened. I picked this area in South Houston because 8,000 homes were flooded in this neighborhood. And the simulation that, again, which is pretty realistic of the flood that was, is on the top right. I show a map here for those of you who know what Houston is. I've never been to Houston, so I don't know much about the local layout. And if we use that really lowest estimate, that Clausius-Clapeyron, which was the lowest estimate across all these papers, you can see that the area doesn't change much. This is the flood depth, and so it doesn't look very different. But it is actually, it's about a foot deeper. So there is, an impact on the houses that were flooded. But if we look at the highest statement, that 38% statement that Mark and I made, then you can see there's a huge difference in the flooded area. And so if you lived in, so this area where I don't know if you see my cursor, but there's sort of like a little V there. If you live in that area, you could say, well, geez, if precipitation was increased by 38%, then without climate change, my house would not have been flooded. So it gets, to a really kind of a binary question that has a condition to it. If climate change affected precipitation by this much, my house was flooded or not. And the depth actually on the right here shows that, if this was the effect of climate change, that, the flood was almost 6 feet deeper. So the best estimate of all those three papers was 19%. That's what I'm showing here. The flood that was, and the flood that might have been if climate change increased precipitation by 19%. And of course, it's less area because there's less rain within the world that might have been. And the best estimate of the insured losses from the reinsurance companies is that Hurricane Harvey cost $90 billion. And so my first crude estimate was, well, that 19% increase in rainfall across greater Houston area led to a 14% increase in the area. So you could say, well, okay, 14% of $90 billion is 13 billion. That would be an assumption that everything was equally valued and everything was equally distributed across the area, which of course is not true. And we'll revise this statement in shortly. But we can say for that, and this would be something that insurance companies might be interested in, is that the probability of an insured $90 billion loss in Texas was quadrupled because of climate change, because that risk ratio associated with a 19% increase is about 4. But we can do more than that. Now we can go from the actual flood to what did that do to houses? And a young colleague of mine at Louisiana State, Kevin Smiley, took those data. Oh, I should have said that this flood model here, which is a hydraulic model, is actually extremely computationally fast. So the resolution of this is 30 meters, which is about the size of a suburban house in its yard. So he took that data and he took it to real estate and census data and came up with this picture and showed that the density of homes that were flooded is not uniformly distributed. In fact, people tend to live near the water, and so those were places that were impacted more. And so that for that 20% change in precipitation, that led to 32%. That led to about 14% flooded area overall, but it led to 32% more homes flooded in Harris County where Houston is. He also found that 75% of the flooded homes in the flood that were outside the 100-year floodplain and thus not required to have flood insurance. And I think partially this explains why NOAA's estimated loss is 155 billion. Now, if we assume that all those losses are from structures, and I'm not sure because NOAA doesn't actually tell you too much about what this loss actually encompasses. But then 1/3 of that damage, because 32% more homes were flooded. So then instead of $13 billion, our new revised estimate is $50 billion. Now this could be refined more if one went in and said, okay, houses in this area that were flooded were worth more than houses in that area, but we have not done that yet. He also used census data to look at socioeconomic factors, and he looked at income and race. He looked at single versus multifamily residences, looked at mobile homes. Didn't see too much differences between the two factual and counterfactual scenarios in the latter two, but he found big ones on income and race. And in particular, what we found is that about half the flooded homes, either with climate change or without climate change, were low-income Hispanic households. But the background population is only about 1/3 Hispanic households. And so this is really a quantification of environmental injustice. And because these low-income Hispanic communities were disproportionately affected. And we also found some other unusual things that we think we can interpret. In the high-income, mostly white neighborhoods, the richer you were, the greater the financial damage you experienced. But somewhat paradoxically, in the low-income Hispanic neighborhoods, the poorer you were, the greater your relative financial damage was. And we think what this is that both of these groups live near the water. The rich people, live places where they had a nice view, and so that commanded a lot of, higher, more expensive homes and what. But the poor people live closer to the refineries, and so those would be, low. The poorer people would live in those areas. And oddly enough, we found no statistical significance in non-white, non-Hispanic neighborhoods, particularly African American neighborhoods. And our explanation of that is that the African American population has been in Houston for a longer period of time than the Hispanic population, and so the new arrivals, were forced to live in places that were more vulnerable. So I call this end-to-end attribution. So a degree of global warming in the Gulf led to about 20% more rain, which led to about 14% more flooded area, which led to 32% more homes flooded, or actually that should be 50 billion, I'm sorry. So I call that an environmental injustice. Now, we recently submitted a paper on Hurricane Ida's remnants, and we looked at this in more detail, and we found again that low-income households were disproportionately flooded compared to the background population, and that climate change actually exacerbated that when we looked at deep floods. When we looked at shallow floods, which is what we did here, we didn't see that climate change affected the percentage of the population that was affected. It certainly affected the numbers. But when we looked at deep floods in Pennsylvania, New Jersey, and New York, we found that the percentages changed even worse. And so, and deep floods, of course, are more damaging, especially as they get above the electrical outlets. Then you have all sorts of more repairs that are necessary. Now, that 30-meter flood data is publicly available if you'd like to mess around with it. And these are some of the papers. So I'm going to shift gears and talk about temperature change. That first plot that I showed you is reproduced here. Here's just from a paper I wrote some years ago where I looked at a couple of different models, did these experiments. You can see there are some model structural differences. In particular, this MyRock model, which is a Japanese model, has a very hyperactive sulfate aerosol forcing. And what we see then is that actually human interference made heat waves in Asia, where there's a lot of air pollution, colder. And I think there's some realism to that. I mean, if you've ever been in Beijing on a bad air day, the sun doesn't shine, so it's not hot. And the conditions for a bad air day, high air pollution data, are very similar to those for a heat wave, for the meteorological conditions. But one of the things, the reason I put this picture up here again is to talk about uncertainties. And what you can see is that these two curves, the red and the blue curve, are not quite parallel, but they're close. And so the change in the magnitude question, when you draw those vertical lines, they're different at different return periods, isn't very different. And so uncertainty in the change in the magnitude of a heat wave is relatively insensitive to the uncertainty in your estimate of how rare it is. And so I make a statement, and I'm going to make this statement to Congress, to Senate, that every heat wave of reasonable rarity being like a decade or so, from now on in the United States is somewhere between 2 and 5 degrees Fahrenheit warmer because of climate change. I don't need to know how rare it is in order to make that statement. But for the change in probability, actually, it's quite different, because you have to use your imagination here. But because of these curves are relatively flat, if we went from, say, 106.8 degrees to 107, it would be way out here. It'd be maybe 2,000, 3,000 years. And so the uncertainty in that risk ratio, the change in the probability, is actually very sensitive to uncertainties in the magnitude. And of course, none of these things are written absolute. I mean, there's always an observational measurement of uncertainty. Staying on heat waves, I want to use this 2021 heat wave to show you a little bit more about statistical counterfactuals. This heat wave will probably be the most written about extreme weather event of all time. There are at least 20 papers on this, of which 3 are by me and co-authors, but I think there'll be 30 or 40 by the time it's over, because it was such a complicated event. It was such a rare event. It had what they called an omega block, or the heat dome, and it was in a place where they really don't happen very well. They never happened before, over British Columbia. It was compounded by the fact that a rare summer atmospheric river brought some latent heat energy into the region. It was also exacerbated by, there was a drought in Oregon and Washington, and of course climate change. So these are all some of the causal factors that that cause this thing to be a 4.5 sigma event. And you can see it here, in this. These are 2 areas that we looked at. This is the area of the paper I'm going to talk about, just the United States. The WWA, the Freddie's Otto's organization, looked at a bigger region, but you can see that it's a clear outlier compared to 2021 compared to any previous year. And so if you do a simple generalized extreme value analysis using only one covariate, the greenhouse gas, or at just even time, which is what some people do, or global mean temperature, just to represent the human effect, and you do an out of sample event using data from 1950 to 2020, or even 1920 to 2020, what you find is that most of the stations, or many of the stations, especially as you get into Canada, exceed the upper bound of this bounded generalized extreme value distribution. And in fact, they even exceed the upper bound of the upper bound by if you put a 95% confidence interval on that upper bound, they're above that. And so the WWA made a statement, it was impossible with climate change. It's actually, if this was the only thing that you had, you'd say, well, it's impossible even with climate change, because it's above the upper bound of this. And so obviously something's wrong, because the event happened. And so what the WWA, when Garrett Young was still alive, what he did is he said, well, let's just put the 2021 value in it and do an in-sample fit. And one of the things we showed was that actually does such violence to the fit of this new GEV that we really just don't believe anything. So we have this paper that's in archive now, and I would encourage you to take a look, where we try to solve this problem. And the solution that we found is just add more physics. Before, the only physics we had in this was the greenhouse gases. We added some more covariates. The first thing we did is added a temporal only dependence. We had the greenhouse gases, which is uniform for all the locations, and then El Nino, which is also uniform. We then further put some more temporal dependence in it by looking at drought, but that also depends on where you are, because the drought in Oregon wasn't as bad as in Washington, for instance. And so, that's spatial and temporally dependent. And then we also found we had to use urbanization, because from 1950, there's been a lot of urbanization in the region, particularly around Portland, apparently. And as you pave things, you can change the albedo and the urban heat island is basically an effect we tried to account for. We also put in some spatial statistics, and there we had some covariates that didn't vary in time. We looked at the mean climatology of precipitation, because the coastal areas are wetter than the interior of say Washington State and Oregon. We also looked at topography, which added 3 more covariates: elevation, slope, and then the direction of the face of the mountains. And also, perhaps somewhat duplicative of the climatology, we also had the distance from the coast. And then finally, we imposed a copula on the spatial statistics, and this is the part I know the least about, so don't ask any hard questions about that. But from the paper, we imposed a copula with the stationary Gaussian process with standard Pareto margins, and you'll know what that means more than me. And we looked at 4 different statistical models, and I'm going to show you those here in a moment. 1 through 4 labeled. The first one is that thing I talked about at the beginning, where we only looked at the greenhouse gases. We looked at all the stations. The crosses are where the observed temperature exceeded the upper bound of the model distribution. And the number in the corners here in the left-hand corner is how many of those, what percentage exceeded that upper bound. And you can see in that simple model, almost 40% of the stations are impossible. The next one, we added all those temporal covariates. Those the greenhouse, what was it again? Greenhouse gas, El Nino, drought, urbanization, and it didn't help as much as I thought it would. It only reduced that to almost 30%. And so then we put in that climatological dependence and the spatial statistics, and that brought it down to about 10%. But it was a copula that brought it down to just 3%. So we still have some outliers, but actually none of these stations exceed the upper bound of the upper bound. And so in some sense, we think we've solved the problem. Now, the fact, the real world is the above, is the where we have everything set to 2021 values for all these spatial the temporal coefficients. Then we made a statistical counterfactual, much more complicated than what we did for Hurricane Harvey, because instead of 2 covariates, now we have 4 that we could vary. But I think we only varied 2. We only varied greenhouse gas and urbanization. And what we could see when we have all the bells and whistles, that now a bunch more of the stations are impossible statistically. And so some of these stations, one could say, well, this temperature was impossible without climate change. Not all of them by any means. So the statement is considerably weaker than what the WWA wrote in its rapid attribution station study, of which I was a part of. So going from heat to impact, the weather to impacts, you can also ask, how many people died, and you can exploit these curves of mortality risk versus temperature. And this gets back to the magnitude question. Now, you might have thought that, a 2 degree or 3 degree Fahrenheit or even centigrade change in the temperature isn't very much, but actually it is, because these curves are so steep as you get to high temperature values. And so the risk of dying at 105 degrees is quite a bit lower than it is at 108 degrees, for instance, depending on where you live, of course. So a simple way of estimating this is just go to this curve and say, okay, climate change caused, 2 or 3 degree change in the temperature. And then you can read off the graph, what the change in the risk is. So the mortality in the world that was and the world that might have been, you could compare and say X number of people died. Dan Mitchell in Bristol did a similar kind of thing, where he actually used that mortality curve to transform the temperature return value curve that I showed to mortality return value. And for the 2003 European heat wave, which was the first study actually of any event attribution study to be made, they found that the chances of the level of mortality was tripled because of climate change. And then, of course, this was 2003, and the amount of climate change in 2003 is a lot less than now. They estimated that 500 people died in Paris because of climate change. But there are 70,000 excess deaths in this heat wave. And, because hundreds of millions of people were affected by it. And so, the actual number of people, the whole of Europe that died in this event because of climate change would be much, much larger. But one of the things I learned recently is this is very hard to do in the US because medical privacy laws don't give us all the data that we need to generate these mortality curves. I talked to I've forgotten her name now right off the bat at the top of my head, but she told me that she only had data, and she has the best data in the world, and she only has it out to 2006. When they did these kind of studies, when they did these kinds of analyses in European cities, and they looked at, say, the last 10 years compared to the previous 10 years, there's quite a bit of a decrease in the mortality as time goes on. And humans are very adaptable. And, they know now in Europe that these temperatures are very dangerous. And so they've taken measures to reduce the death curve. And so to reduce mortality risk. And so doing this for the Pacific Northwest heat wave is very difficult because we don't have that kind of data. And I should add, and I don't know the details, but there's a lot of statistics that goes into taking that mortality data and temperature data and developing these curves. So we sort of have, kind of different kinds of questions we can ask with the impact, the mechanistic statement that climate change flooded 32% more houses or killed 500 more people, or the risk of the Harvey event was quadrupled, or the actual death rate was tripled. Or there are these binary questions, like my house was flooded or wasn't because of climate change, conditional on the statement that climate change increased the weather change by a certain amount. And this is the question for there's some disaster in Libya where many, many people died. Some dams broke, 2 dams broke, and the press release was all over this because there was a rapid attribution study on rain that said it was increased by such and such amount. And the press was all over it saying, well, climate change killed all these people. And that's actually something we don't know, because maybe the storm without climate change would have been a big one in Libya. And the dams might have broken without climate change. And so until we know that, you can't really make a statement about whether climate change killed these people or not. So I want to shift gears and finish up with loss and damages. And this is the flood in Pakistan recently. And it's motivated by a recent paper that my colleague Andrew King wrote that we thought was misguided, where they said that event attribution is not ready for a major role in determining loss and damages. And I'll get into what that is in a moment. Our paper is a rebuttal to this, and we basically say it is. And this is going to appear shortly in the same journal. And in the COP27, which was last year in Egypt, and the COP28 is coming up next month in Dubai. That's a conference of parties for the United Nations Framework on Climate Change Convention, I think it's called. And the decision was, and I quote, establish new funding arrangements for assisting developing countries that are particularly vulnerable to the adverse effects of climate change. The key word there is particularly vulnerable. What is that going to be defined? Other aspects that I've read still need to be decided, and apparently they're not going to be ready for COP28 is who's going to give the money, who's going to get the money, and for what kinds of things. And so we asked a question, what kind of events are important in developing nations in general? And from the World Meteorological Organization, the WMO, looking at the top 10 most deadly event and expensive disasters from over the last, 50 years. The expensive ones are all in the rich countries, of course, because they didn't normalize to, say, nations' GDP. Because if you did that, you'd find something very different. In fact, and those are heat waves usually in the West. But in developing nations, the largest cause of death is famine, and the weather disaster that leads to famine. Other causes of famine too, of course, politics being a big part of it, but agricultural drought. So deficits in soil moisture lead to crop failures. Close behind that are tropical storms, hurricanes, with 500,000 people dying at least. And then other kinds of floods, like that flood in Pakistan, was not from a tropical storm. And then heat waves they estimated as 4 on this list, but we think that that number is actually severely underestimated because heat wave deaths don't always happen right after the heat wave, and most of these countries don't have the wherewithal to actually do the counting. But the point of what we try to make in our paper is that all these classes of events are the things that attribution does well. Now, Andrew talked about all sorts of events that are important in the West that we don't do well, like tornadoes. But tornadoes don't even kill that many people in the United States compared to a moderate, or the damages aren't anywhere near the same as they would be for a moderate-sized hurricane. So these things we do well. So the demand is clearly there. The fact that they established this fund shows that there's demand, and we fear that Andrew's piece undermines that urgency, which is why we wrote our piece. And the alternative is, if event attribution is ready, what are you going to use? And the only other thing that really is out there are these Dice Nordhaus kind of models, macroeconomic models, which uses a damage function, some constant times the global mean temperature squared. And the latest constant, it used to be lower in the original Nordhaus, is this number right here, which is from Potsdam, I think. And so I went back to Hurricane Harvey and looked at what the GDP of the United States was in 2017, and the damages would have been $80 billion from climate change for all the climate change impacts over the United States, which is actually, Harvey was, arguably twice. Harvey was arguably half of that amount. Well, there were a lot of other disasters in 2017. And, I'm not a macroeconomic person, but why would you expect this constant to be the same for the United States in a very poor country, one that arguably is very in the particularly vulnerable category of Burkina Faso, which is in the Sahel? That doesn't make any sense to me. But I think another problem that with Andrew's piece was some naivete. And I quote the IPCC, it is to provide information, the Intergovernmental Panel on Climate Change role is to provide information to government that they can use to develop policies. And these claims to a loss of damage fund will not be settled by me or any other climate scientist. It's rather a political process. It would be highly negotiated. And so I think that's one of the things that we have to realize, be a little humble here, is that we're not the ones making the choices here. We're just telling them what we know or what we don't know, which is equally important. And I think to make some of this more credible, we really need to engage physical and social scientists from these nations. And one thing I have learned is that when you do that, you do a much better study, because the people that live in these countries understand, not just the meteorology, but the social bits a lot better than I ever could, or than anyone could from the Western nations. You got to live there to really know. So here's our straw man for how this process would work: is that there'd be some political negotiations about how much money is going to be available. Then someone would decide who is actually eligible. I think that's a kind of a difficult question. And then which kinds of events would allow these eligible countries to make a claim. This is where the event attribution would inform, and then the funds would get out there. So we'll see what happens in the COP28. I mean, usually, I was told by a wise person, expect the worst, then you're not disappointed. And so I do expect the worst. But on the other hand, the COPs have surprised us. The establishment of this fund in COP27 in Cairo was a surprise. I don't think anybody expected that to happen. They've been talking about this since 2009, and all of a sudden it happened. And the Paris Agreement that set the global warming level targets of 1.5 and 2 degrees is a similar kind of surprise. And so hopefully we'll be surprised and that there'll be some progress on this. I'd like to conclude, trying to motivate why statisticians are necessary. But first to say that there's a lot of room for advanced statistical methods, but it's hard. And it's challenging for a couple of reasons. One is the language. I probably use some words today that you may have very different usage. So language is an issue, or vernacular are different. There are also institutional barriers, because, both at the funding agencies and at institutions, at universities, it can be hard to work across departments, even harder to work across colleges, and so, social scientists, often are very separated, for me, so we don't have these kind of social scientists at the lab. We have to go to other institutions. So that's hard. But there are some really interesting things, and I put the things that are interesting to me, but I think there's more. And Mikhail and I were at this meeting in Granada, the BERS meeting in Granada, and spatial statistics were the thing that was discussed the most. And I've really learned a lot about how useful these can be. They're computationally expensive, and I think there were some things we learned at that conference about how they make them less expensive. But they can real insights about the spatial scales of extreme weather, and I think that's interesting. And there's a lot to be done there. Something that I've been interested in for a long time with Dan Cooley are multivariate statistical model, extreme statistics, I suppose. But it's that sometimes for these kind of compound events, it's rare combinations of variables rather than the variables themselves that are interesting. And my example is hot, dry, and windy versus hot, moist, and stagnant heat waves. The meteorology on these two kinds of events are very different. The impacts are very different. The first one is windy ones, or dry ones are risk of fire, whereas the moist, stagnant heat waves are risks of dying from heat stroke and other kinds of kidney failure, renal things. And what some people have done is, and sometimes it works, is to use a copula. But for some of these examples that we're interested in, we don't think that that's the right way to go, because the available copulas are imposing a distribution or imposing relationships that may not actually be there. So Dan has a non-parametric method that I have a student working on right now as well. I think there's an awful lot to be done with causal inference techniques that we haven't exploited. One technique, I think there are others, are this thing called graph networks. And then I would be remiss if I didn't say something about machine learning. At Berkeley Lab, we were very successful until Prabhat left for IBM to use machine learning as a diagnostic. And I kind of call this the Facebook app, where we show in a picture and we say, find the tropical storms here, find the atmospheric rivers or the fronts. And this is a supervised feature detection. And we never, before Prabhat left, we had talked about maybe, trying to let you do unsupervised feature detection and have it tell us things that we didn't know. We never got there. There's also, and this is actually still, I think, these supervised feature detection is actually extremely useful for us. Counting the number of storms of a certain type, for instance. But there's also a more prognostic interest in actually developing machine learning climate models. And the example is NVIDIA's ForecastNet. I remain skeptical. I think it's promising. The result, I listened to a talk yesterday, which surprised me that they've been able to do multi-decadal simulations that are stable. I think one of the questions that arises here is, machine learning is very good for telling you things that that are in the training data set. But what we want to know is outside the training data set. And that information comes through the boundary conditions. So for this ForecastNet, for instance, the sea surface temperatures are a boundary condition. And so, as the world warms, we would change that boundary condition. Does the machine learning model then provide credible results outside of, when it's trained on just the existing observations. And that, I think, is an interesting question that I don't know the answer to. And finally, I want to plug the journal that I started some years ago called Advances in Statistical Climatology, Meteorology, and Oceanography. We call it ASCMO. Here's the website. It is intended to be a bridge journal between statisticians and physical climate, meteorological, and oceanographic scientists. And we do about 20 to 25 papers a year, so it's not a big journal, but I think a lot of the papers are really quite interesting, and it is a place where these kinds of cross-disciplinary articles are very, very welcome. So I would encourage your submissions. So thanks much, and I hope we have time for questions.
All right, excellent. Thank you very much.